Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, yet again, we're dealing with 3D force reduction. But as I kind of hinted to in the last tutorial, instead of ending our force reduction with a single force and a single moment, we can actually take that a step further and just cut it down to a single force. Because as you guys know, if I have a force and a point, and I start moving that force away from the point, it'll start to create a moment. So what our goal is in this example is to move our resultant force to a specific area in the XY plane so that that distance it creates with the point will create our resultant moment. And this is a very common exam question. It's very, very good because you have to determine coordinate points. Coordinate points, they love to test because they teach you very, very, very little about it in lectures. So when you find it on an exam, it's like, oh crap, I have no idea what to do. So with that being said, I think it's best to just jump into it so you guys can kind of get what I'm saying. And yeah, we'll go from there. All right, let's begin. Alrighty, so looking at this example, it says if FA is 7 kilonewtons and FB is 5 kilonewtons, represent the force system acting on the corbels by a resultant force and specify its location on the XY plane. So this is very important to specify its location because the first hint in the question is it says it just wants a resultant force. It says nothing about a resultant moment. And then to kind of add to that, when it says specify its location on the XY plane, that usually means we have to move our resultant force around so that it produces our resultant moment. So this question is very similar to last time, where we want to take all these forces and represent them with a single moment and a single force. However, the only trick to this one is, from last time, is we have to move that force around to get rid of the moment, if you know what I'm saying. For example, in 2D, let's say that I have, let's just go here, I have a point. And on that point, I have a force, so let's put a force on here. And then I also have a moment. Well, I can actually represent this as the point, so the point stays. But then all I'm going to do is actually, it'd be the opposite way for this case. So the point will stay, but then I'm going to move the force a certain distance away from the point. So this will be the distance away from the point, so that the force actually creates that moment that we've seen before because it's moved at a distance away from the point. And of course, the force times the distance there will equal the moment. So what's going to happen in this case in 3D, let's just erase all this real quick, is we're given an XY plane. So I'm just going to draw X real quick. I'll draw Y real quick. And what's going to happen is we're going to want to find, oops, oh, I don't even know how I did that, but that's pretty impressive. I'll go back to this color. I'll have to check that out later. All right, so what we're going to want to do is we're going to take and find a resultant moment and a resultant force about this point. So let's say that at that point there we have a force vector F like this, and then we're also going to have, and I don't know the directions, I'm just making this up. So let's say that we have a moment vector like this. So this is what we would have found from last time, that the sum of the force combination of all those forces is equal to a resultant force as well as a resultant moment. However, what we're going to do in this example is we're going to take it a step further, and we're going to move the force vector to a different location, say this location, and so that this force vector cross, so this is our new force vector, and if we were to cross that force vector with the position vector from, let's say, A to B, so A to, I guess, yeah, position vector AB. So if we were to go position vector AB cross our force vector, that's going to actually give us the moment vector that we had before. So we're just taking this a step further by moving our force vector to eliminate that moment vector. So the process is actually very, very, very similar to as before, where all the first steps we're going to do exactly the same. We're going to find both the resultant moment and the resultant force about that point O. And then after that, we can do some manipulation, of course, to find the rest. So This example is also very, very good because it shows a little trick. And this trick will save you a bunch of time in the midterm if you know what you're doing. If you don't know what you're doing, it's going to take a long time because as we look in this example, we have 4 forces. 4 forces. And the first thing I think of is, whoa, that is a lot of cross product. I don't want to have to do cross product 4 times. So there must be a simpler way to approach this question, and there is. And the reason why this simple way will work is because all those forces are parallel with the z-axis. And you go, okay, well, parallel with the z-axis, that's great, but why do I care? Well, let's just draw it in 2D and see what happens. So let's draw the z-y-axis. So this right here, the z-y-axis. So if I were to go in 2D here, I'm going to make my z-axis, and I'm going to drag this one all the way across. So this is my 2D case. I have positive z here, and then of course I have y on this side, and then on this side it'd be negative y. And let's just put those forces onto this axis and just see what happens. So let's pick, I don't know, dark green. Why not? So as we can see, we have 2 forces on this side, and we have 2 forces on this side. And of course, it's not really to scale whatsoever. It's just for demonstration purposes, so you guys can see exactly what I'm talking about. So we have our 4 forces, and of course we need to label them, how much they are. So starting at the very, very left side, the furthest one away is FB, which we know is 5 kilonewtons. So I'm just going to put 5 kilonewtons, and that's followed by the 6 kilonewtons. And then moving on to the other side, the closest one to, I guess, y equals 0 is going to be FA, which is 7 kilonewtons. So we're just going to put 7 kilonewtons. And then the last one, of course, is going to be the 8 kilonewtons. And it just so happened to work out where it's 5, 6, 7, 8. So I guess that's just a coincidence. So another thing we can do real quick is we can just label distances. So our first set of distances will go something like this. And if we look up, we see the distance from point O, or I guess along the y-axis, to FA is 600 mils. So we know this one's going to be 600. If we go back and look at the 6 kilonewtons, we know it's 650. So let's just put 650. And then let's find the distances to the further forces. This will be something like this. If we're looking at the 8 kilonewtons, we see that it's 700 away. And if we look to the other side for FB, we see that it's 750. So I didn't really have room for millimeters in some spots, so I'm just going to put a star and put millimeters. All right, so if this was your 2D problem, and you had all these nice, beautiful forces, and I asked you to take the moment about the point O, which is the purple spot right there, there we go, point O, you guys would do this no problem. It'd be nice and easy for you guys. You guys know exactly what you're doing. It's just 2D moments. You're already given that perpendicular distance, so it's actually really not too bad whatsoever. So just for fun real quick, because that's what engineering really is, it's just a bunch of fun, is let's just take the sum of the moments about point O and just see what we get. So starting on the very, very left side, we're going to, of course, have 5 kilonewtons as times 0.75. I'm just converting things to meters. And then, of course, that would cause a counterclockwise rotation, so it'd be positive. So we're going to go plus the 6 kilonewtons times 0.65. And then that would also be a I can't even speak right now. That'd be a counterclockwise rotation. So that would also be positive. And we're going to have to go to the other side. So we're going to just go minus 7 because it's going to be a clockwise rotation, in this case about 0.0. And that's times 0.6. And then we're going to go, go down to the bottom line. Minus 8. And then that one is going to be times by 0.7. So if I were to do all that math, what I'm going to get is a moment of negative 2.15 kilonewtons per meter. So then you ask, okay, well, Clayton, why did we do this? We get a moment, sure, but what is it? Well, this is when you have to remember what you know about moments. So what happens is if we take a moment in two dimensions, so we're used to taking the moment in the xy plane. That moment will actually be the moment of the perpendicular axis. Okay, well, what does that mean? So let's think about 2D. If we're in the xy plane, xy, and we take a moment, and in 2D we just say it's moment, but it's actually the moment about the z-axis. It's about that axis that's perpendicular. So if we were to look at what we have in this figure here, we have the y and z-axis. So what's the axis that's perpendicular? Well, that's the x-axis. So this right here, this negative 2.15, oops, zoomed out, that's actually mx, the moment about the x-axis. So that's actually very, very nice. Instead of doing all that cross product to find the resultant moment or its component in the x direction, I just went right to it. And it's nice and easy. So we can also do that with the other axis in here. So let's just go, let's go one more real quick. Let's go the z. So I'm now highlighting this one in blue. Let's go the z x-axis. So this will be number 2. So we're going to go down here. I'm going to draw another axis just like before. This one's going to come across. So again, nothing new here. This is z. If we look at how it is, the easiest way for me to see it would be this is x, this is negative x, and we can draw all the forces. So I'm going to go to, I'll go dark blue. Actually, dark blue and blue, I'm an idiot. That would be terrible. Let's go orange. So it's kind of the same as the z y-axis. So we kind of have two forces on both sides like this. Ta-da! Ta-da! Alright, and we all know that they're also both going downwards. So, something like this. So boring, I know, but... Alright, here we go. So we got our 4 forces going downwards. Now we're just going to label them. So let's find the one that's furthest along the positive x-axis. And that looks like it's going to be FA, which is 7 kilonewtons. So I'm just going to come here and write 7 kilonewtons. And then the next one's going to be the 6 kilonewtons. So 6 kilonewtons. Moving on to the other side, let's look at the one that's furthest along the negative axis, and that's FB, which we know is 5 kilonewtons. So that must mean that our last one, the 8 kilonewtons, that's right here. So let's just go 8 kilonewtons. 8 kilonewtons. So like before, we can also dimension these. So we're just going to go like this. We'll draw 2 lines. Ta-da! Like so. And we know that for this one, it's kind of very similar. They're both 100 or 150. So the closest ones are going to be the hundreds, 100 mils. And the further ones are going to be 150. And just put my units off to the side so everybody knows what I'm talking about. So we can do the exact same thing we did before and start taking the moments about the center point. So what did I do the center point in? Purple last time, so let's stick with that. So remember, this is still point O right here. I'm just going to put O, and what I can do is I can sum the moments about O. So right here, I'm just going to go sum of the moments about O. So I'm just going to take it for all those forces real quick. So working our way from left to right, we got the 7 times 0.15 plus 6 times the 0.1 minus 8 times the 0.1 minus 5 times the 0.15. So same process as before. And what happens is I get a moment of 0.1. So 0.1, and the units would be kilonewton times meters. Now, again, the moment that we take in 2 dimensions is about the axis that is perpendicular or out of the page. So the axis in this case that's out of the page is the y-axis. So we know that this is actually my. So again, we just found our resultant moment in the y component, resultant moment component. Oh my gosh, this is going to get to be a tongue twister by the end of it. but we found the y component of the resultant moment. Well, it just sounds so bad. But you guys see what I'm saying? Or this is kind of the nice easy trick, because this beats the hell out of doing cross product 4 times. That would be terrible. If you're doing cross product 4 times in your midterm, something's wrong. I don't even think the meanest professor in the world would do that to a student. So, yeah. All right. So now we have x, mx, we have my. Now we have to ask ourselves, well, what about mz? Well, we can actually do the exact same thing and write another axis. So what I can do in purple is I can write my x and my y-axis like this, and I could draw it out, but what you'll find is there's no forces in it, because all the forces in the xy plane go into the page. None of them have an x or a y component. All those forces are just z components. So if that's the case, and I were to draw the diagram, there'd be nothing on it, we can conclude really quickly that the moment about the z-axis is 0 kilonewtons times meters. So, from this, actually this looks like M2. I'm just going to put a little bit of thing in there. So, from here we can actually put that our resultant moment is just going to be those 3 components that we already found. So looking up at mx, we got negative 2.15. That's in the I direction. Plus 0.10. And that's in the j direction. And then plus 0 in the k direction. So we actually found our resultant moment really, really fast, even though there was 4 forces. And of course, depending on how quick you write, how quickly you type in your calculator, finding the cross product 4 times, that will work too. It'll give you the exact same answer. So if you're saying, hey, you know what, Clayton? 2D sucks, 2D blows. Well, actually, you're going to hate the second half of the course if you think that. But if you want to do the cross product 4 times, it'll give you the exact same answer, no problem. Let's say that you're a little unsure of this method, may not know which dimensions to pick, something like that. That's perfectly fine. Then you can easily go back to the cross product as a check. Completely up to you. So what I'm going to do now is, remember in the steps, the first one was find all the moments, find the resultant moments. So we actually kind of skipped, we did steps 1 and 3. So let's just go think about step 2. We need to find the resultant force. So we have our resultant moment. We need a resultant force. So we know that Fr is going to be equal to F1. That's going to be all the forces. So we got F1 plus F2 plus F3 plus F4. Now this one's also easy because, as we discussed, those forces go in one direction. They have no x component and they have no j component. So all we have to do is just add up all those forces. So what we get in brackets is 0i plus 0j, because remember, none of those forces have an x or a y component. And it's going to be minus because all those forces are going downwards, and we're just going to add up all the forces. So 5 plus 6 plus 7 plus 8. And what we get is negative 26, so minus 26k. Ta-da! And the units were kilonewtons. So now, with a resultant force and a resultant moment, if I were to draw kind of an origin like this, just give me a second, let's just try and make it somewhat nice. I know I'm not the best artist, but whatever. Alright, so if this is our origin, so we have our x, our y, and our z. Now, is that how it is? Oh, they drew an isometric. Alright, oops. I'll go back and... Alright, let's just fix all this. Here we go. Let's do it exactly how they drew it so there's no confusion at all. So they kind of drew it like this. I like how I say no confusion at all, but yet I'm probably making it 100 times more confusing for all of you guys. So we know that there's z's going up. We know that x is going to the left, y is going to the right, so this will be x. This would be y. And what's going to happen now at this point in time, at point O, right at the center, we found our resultant force, which we know is just going in the negative direction. So this is our force vector. And we also found a resultant moment vector, which is in two directions. So it's in the negative x, but positive y. So it's, let's just say it's something like this. Remember, these don't have to be to scale. Nothing like that. It's just kind of show. So this is what we have now. We have all of our forces represented as a single force vector and a single moment vector. And I guess I might as well put r's. So now the question arises, where can we move that resultant force vector in the xy plane so that it results in that moment vector? So I want to take this fr right here, and I just want to move it. I can move it right, I can move it left, but I want to keep it in that xy plane so that it creates that moment. So how do we do that? Well, let's just kind of think about how to get a moment first of all. So if I wanted a moment vector, well, we know that's going to be equal to a position vector cross a force vector. And we already know that the moment vector we're interested in is mr, the force vector we're interested in is mr. Now, we have to try and think, okay, well, the position vector, it goes from a point to another point. And we know that we want the moment, that moment vector that we have is about point O. So we know that the force vector, position vector must start at point O and then go somewhere. But we don't know where it goes. So what I'm going to do is I'm just going to put the second letter as P. So up here, I'm just going to put a dot. I'm going to label this P. And we don't know what P is. P is the distance we have to move that force vector to get the moment vector. So the coordinates of P is I'm just going to put X, comma Y, comma 0. So it could be anything in X, it could be anything in Y, but we know it's on the XY plane. So I'm not going to put Z because we know that that must be 0. The point must be on the XY plane. So what I recommend now is just solving for the coordinate points that we did before. So what we can do is we're going to set up our matrix and we're going to solve systems of equations in the end. But before we do that, we have to find the position vector ROP. Well, it's actually pretty easy because what we'll find is it's RP minus RO. And remember, since O is the origin, everything is 0, we can just cancel that crap out. And we know this is going to be equal to X in the I direction plus Y in the J direction plus 0K. And I'll have units of, let's say, meters. Why not? All right, so now we can start our cross product. So even though you thought you got away with it, you actually didn't. Cross product will always come back to haunt you, always. And we know that the top row is always going to be I, J, K. So we're just going to fill that in. We know that the second row is going to be that position vector. So our position vector, well, we don't really know it. It's parametric right now. It's in terms of variables. But what's nice is we can just pretend that those variables are numbers and kind of carry on. So for this, I'm going to put X, Y, and 0. So nice and easy. And of course, our force vector is even easier, which goes in the third line because it's 0, 0, minus 26. So as you guys may kind of guess, this cross product is really nice. A lot of zeros, a lot of stuff just disappears, cancels, whatever. So it's perfect. All right, so doing this, we're going to get a squiggle bracket, and we'll start with the I component. And what we'll see is we're going to get negative 26y minus 0. And that's it for the I. And we're going to go minus. And looking at the j, we're going to get minus 26x minus 0 again. So this cross product should be really simple. A lot of stuff is 0, nice and easy. And for the k component, well, if we cross out the k column, we look that I has a 0 and j has a 0, so we just know this is going to be 0k. And the bracket, and this is going to have units of kilonewton meters. So from here, we can kind of take it a step further and write down what the moment vector is in kind of a nicer way than this. So we know it's going to be negative 26y plus 26x. And I guess I need to put in the j direction, stuff like that. Yeah, so Don't pay attention to me, I'm just being an idiot right now. X, and that's in the I direction, plus 26x in the j direction, and plus 0k. So now we have a moment vector in terms of x and y. So how do we solve that? Well, we go back to what we know. We actually know what those values in that moment vector should be. We know, and I'll just do this in a different color, that this negative 26y, well, if I go up here, we know that that should actually be equal to negative 2.15. We know that the 26x should be equal to 0.1, so 0.1. And we know that the k should be equal to the k up there, which is 0. 0 equals 0. All the math checks out so far, so not too bad so far. So now we can go and start making our systems equations. So starting in I, like I said, I got negative 26y is equal to negative 2.15. Well, that's actually as simple as it's ever going to get in life. So we realize that y is going to be equal to 0.082 meters. And we can do the same thing for the j component, so we get 26x is equal to 0.1. We know that x is going to be equal to 0.003. And yeah, we'll add another decimal, 8 meters. So those are actually our final answers, because it said where on the xy plane will this be to create the resultant force. So what you should do if these are your final answers is let's just make them nice, make them in order, so we know that x is equal to something, y is equal to something. Now I don't like the 0.000 blah 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 blah, so what I like to do is just convert it to millimeters in this case, make it a little bit nicer. So we know that x is going to be equal to 3.85 millimeters. And then the y is going to be 82.7 millimeters. So I'm just going to put a box around it because of course that is the final answer that I'm going to stick with. So something like that. But let's just take it one step further, because they could ask that too and they say, okay, well, what did we actually accomplish? What does this mean? So if I were to draw the xy plane again, and yes, I hate drawing it this way, it looks so dumb. Alrighty, something like this. Alright, so we have our z-axis, we have our x, and of course we have our y on the other side. So remember that, and I'll do it up here and just take a quick peek. Remember, this is where we were at, where we had two vectors. We had a force resultant vector and we had a moment vector. Well, now what we did is instead of everything being at point O, which is right there, so that's point O, we found another point which is very little along x but very far along y, so this point right here, and we moved our force vector. So this comes straight down, and this is still the same force vector as before, and we're going to call this point P. So this is still the same force vector as before, so this is Fr. And that distance between O and P, that creates the moment that we see up here. So it's really, really, really nice because we took a very complex force system. It had 4 forces. We broke it down into 2 vectors, a force vector and a moment vector. And we broke it down even further so that it's just a force vector. And that is a good midterm question. They love to test you on something like that because you have to work the cross product backwards. Your knowledge of force reduction has to be through the roof. So yeah, I really like this question. Good midterm question. And that's how you get the final answer. Now, I really wish I can tell you guys that this is as hard as it gets. But this is actually still kind of nice. As you will see, there's a very, very special case coming up. Next video, very important. It's called a wrench. And the wrench is just the worst thing in the world. But I'm going to explain to the next video. I kind of been keeping it a secret from you guys, and there's a reason why. It's because it sucks, and you guys are going to hate it. But if you guys can do this example, if you guys can do the last example, you're good for almost every case besides the wrench. So we're going to get into the wrench next video. So until then, thank you guys all so much for listening, and I will see you guys in the next video.